Hi, I'm Katja. I'm the team manager of UCL Rover under UCL's Mechanical Engineering Department. And this year we are proud to present our rover, Sparrow. Our team consists of 25 members from undergraduate degrees ranging from mechanical and electrical engineering, computer science, robotics and AI, and natural sciences, split into 6 sub-teams: mechanical structures, robotic arm, electrical, autonomous and control, base station and logistics, who all work closely together to design and build our rover.
Hi, my name is Amit and I'm the logistics sub-team lead. Logistics' primary role is bringing together the various sub-teams as well as external support. This year, we are extremely grateful to the numerous companies that decided to provide their support through monetary and alternate means, namely RS Components, Autodesk and Realm Insurance. Aside from sponsorship, logistics also deals with all deliverables and documentations produced on behalf of the team, whether this be submissions for the ERC or presentation and leaflets for outreach events, such as the St. Paul's Robotic Conference, where we present to young students, showing them the available pipelines to explore robotics further and inspire them to pursue it. UCL's competed in the ERC all the way from 2018, showing glimpses of success intermittently. However, since then, the team has undergone numerous rebuilds and difficulties. Due to this, we are coming into this year with a completely new design for almost all aspects of the rover, with aims of qualifying as one of the 5 UK teams. We hope to show that a team comprised almost entirely by undergraduate students can compete head-to-head with more established teams with more resources and history, showing that ingenuity and innovation can outperform longevity and over-reliance on previous successes.
Hi, I'm Emily and I'm part of the Science Cash team. Scientific analysis remains a core priority for the geology section of the Science Cash. This year's competition targets the Hellas Planitia, where a bifurcating channel system and exposed layering point to past fluvial activity. These features present strong candidates for deep sampling and astrobiological investigation into past habitable conditions.
Hi, I'm Tracy. I'm the mechanical structures lead. We designed and built the mechanical body of the rover. The chassis was designed as a lightweight aluminum frame that balances strength with mass reduction. The suspension uses a rocker bogie system with a central differential bar, allowing vertical motion on one side of the rover to be transferred to the other. This improves wheel-to-ground contact and helps distribute loads more evenly across uneven terrain. The differential bar was analyzed using FEA to check torsional behavior, ensuring it can withstand forces experienced while climbing slopes, crossing rough surfaces. The wheels were designed using generative design to maximize the strength-to-weight ratio and were 3D printed in TPU to provide additional damping. An interchangeable tire design allowed different tread patterns and depth to be tested. The Science Cache was designed for reliable, deep sample collection. The mechanism uses a C-beam with 2 lead screw-driven gantries. The outer gantry lowers the system, while the inner gantry drives the auger and sample container into the soil. A load cell measures the collected mass in real time, allowing drilling to stop once a 100-gram target is reached. To improve safety and reliability, the system includes an emergency shutdown, fuses, software motion limits, and physical end stops.
The arm has 5 degrees of freedom, 2 at the base, 1 at the elbow, and 2 at the differential wrist. The base provides yaw rotation through a planetary gearbox, which is driven directly into the base plate. Previously, we used a spur gear pair, which had been on the rover since 2018. However, the backlash was significant. Direct drive through the planetary gearbox removed this issue. The upper arm handles shoulder pitch through a linear actuator. While the actuator is the same as last year, it now sits in a new structure. The upper arm is now 2 sheets of metal joined by struts, with a central strut which connects to the linear actuator. This gives us the torsional stiffness we need and provides a rigid mounting frame for the elbow. The elbow uses a manufactured harmonic drive with a 100:1 reduction ratio, driven by a NEMA 23 stepper motor. The previous design was a 3D printed cycloidal gearbox, which suffered from print tolerance issues as well as backlash and not being able to generate enough torque. So the harmonic drive solved all of these issues. The forearm is a hollow carbon fiber tube, which allows for wiring to be routed internally and also reduces mass. The wrist is a differential, using bevel gears to give pitch and yaw at the end effector. It's 3D printed in PLA and driven by 2 servos.
The UCL Rover's electrical system is designed around reliability, modularity and safety. Housed come from a single 6S LiPo battery protected by an 100-amp main fuse placed directly at the battery terminal. From there, power is distributed through XT90 connectors through dedicated subsystem PCBs for drive, robotic arm, and science cache. Each PCB has its own fuse, input filtering, and replaceable drivers, so faults could be isolated without affecting the whole rover. DC-DC converters provide regulated 20-volt, 12-volt, 5-volt rails for Jetson, drone motor, and servos respectively. For safety, the rover includes both a physical emergency stop and a fail-safe relay, while the telemetry continuously reports battery health, current draw, temperature, and subsystem status to the base station.
I'm Ishan, this is Alexander, and we're part of the Autonomy and Control subteam. The rover is controlled by an NVIDIA Jetson with ROS2 nodes for the arm, cache, and drive. The wheel speeds are updated with 6 independent PID velocity controllers. We also have a front-facing 4D LiDAR, which is used for environmental detection. This is able to easily identify nuances in terrain and obstacles in our path.
The resulting point cloud is fed into NAV2, which calculates the trajectory the rover should follow. The rover's position estimate is updated with LiDAR inertial odometry. We also have a vision pipeline for probe detection. Makarim will give a quick overview now.
Hi, so this file will run multiple scripts which takes a video and use SAM3 to detect an object with text description, augments it for different colors and noise, and then it trains a YOLO model to detect those, and you can see how it performs.
Hi, my name is Oscar. I'm here with Base Station to present the Vogelpfeifer communication system. Named after the German word for bird calling system, this design followed the design paradigm to minimize the system to as few moving parts as possible. In order to achieve this, we decided to use a single Raspberry Pi 5 to run as both the visualization and analysis platform via Foxglove, as well as the communication platform via HostAPD. HostAPD runs as a background daemon on the Raspberry Pi 5, allowing for effective communication with the drone at low 5 GHz frequency. This means that even at 100 meters with light interference, we are able to get nice, clean, crisp video footage as well as telemetrics.
Hi, my name is Richard. I'm the drone sub-team lead. So building on last year's design, we made modifications to our drone, ERC 2026. The first change is a new custom carbon fiber frame with 3D printed landing gear and prop guards, with design validation also done in FEA and CFD. We also transitioned to a 6S system with 1750 kV motors and 5-inch props, which enabled us to have a thrust-to-weight ratio of 8:1, as well as a much lighter weight. We also added a H743 FC, and that enabled us to have much better sensor fusion, which includes dual IMU, barometer, and GPS, and also enables us to use PX4, which has a load of safety systems, such as polygon geofencing, automatic landing, and return to home, along with a lot of fail-safe procedures, which include battery loss, signal loss, and GPS.
My name is Amit, and I'm part of the drone sub-team. For our drone's control system, we developed an algorithm within Simulink and MATLAB. The algorithm is then deployed onto a Raspberry Pi 5, which runs it as a C++ executable for maximum speed. The Raspberry Pi is equipped with an IMX500 sensor. The algorithm is centered around the detection of specific Aruka markers within the drone's workspace, and by analyzing and calculating the pose of those Aruka markers relative to the drone camera, we could precisely pathfind to the landing zone. This involved an extensive calibration process within MATLAB to discern the camera parameters. Once the landing marker has been detected and the relative position is calculated, instead, instructions are transmitted to the flight controller using the Mavlink protocol over UART. The flight controller then drives the motors to execute movement smoothly for a landing.